Good morning, everyone, and thank you for the introductions. Again, my name is Phumin Kirawanich from the cluster of the Logistics and Rail Engineering at Mahidol University. Okay, and the presentation is a bit more like a technical, and it pretty much discusses how the local R&D supported the implementation of the metro project in the country, and by looking at the title, it definitely focuses on the area of the EMC research. So first we're gonna take a look the definition of the EMC, and then we're gonna moving into the area of the railway system. Okay, we would start with an accident, and then it's in part of China. I think that was a big accident, as it's involved a couple trains, the collision of the couple trains, and I think there were like quite a high number of the onboard passengers, more than 1,000, and quite a large numbers of deaths and injuries. Okay, so let's walking through the video clip, and then we're gonna discuss. Okay. Is the high-speed train system. Yeah, it was bad. And then, so what do you think? We have seen we call the safety violation, because normally the system it wouldn't allow the two trains occupy the same track section, but is that to happen in the system? And by the investigation, the report mentioned that it was from the failure of the wayside signaling equipment. But in fact, the staff was supposed to stop the train collision by just looking on the big monitor in the CCR, right? And it's also because we have just the lacking of the equipment inspection, and definitely the root cause is from the defects in the design of the system. So we're supposed to have the better design management at the very beginning. Okay, and the cause of this malfunction of the equipment is from the external interference. External source of the interference is by lining. Okay, so if we should have the better design management start early during the railway implementation, it would have stopped this kind of accident. Yeah, that leading to our today presentation. And let's take a look on the presentation outline. So we start with the, of course, just a basic definition and the concept of the EMC. Okay, so the meaning of the EMC, and it's quite important to do the railway project construction. And we're moving a little bit further for the meaning of the EMC in the railway system. And yes, so then we're gonna see how we proceed the project construction and how to do the management of the EMC in the project. And of course, we will walking to how we implemented the local R&D to involve with the project construction of the project, and then we conclude the presentation. Okay. So start with the basic definition of the EMC, and then by just a simple meaning, it stands for the electromagnetic compatibility. It's about it's an engineering term for the electrical and electronic area. So we're talking about something like producing the interference, producing the noise, and the equipment working correctly under this kind of situation, that we call the EMC. And this is what we want. We want all the electronic and electrical equipments can be working correctly together, not gonna interfere each other. So we need to achieve the good EMC in the project. A little bit more information on the EMC, and but we start with some of the keywords. Okay, so it's just a simple traditional keywords like a sources, the one that produced the interference, and we have the victims, like anyone that can be disturbed by the interference, and the environment, because we're talking about the area that this kind of equipment can be working together. Okay, so this is the 3 traditional keywords, and if we focus on this over here at the center, we have the radio receiver. So we have all kind of the interference, and if we're talking on the path or the channel, so you see, interference would be through the air or through the conductor or the wirings. Okay, and from the source of the interference, maybe the infrastructure next to the equipment, or it would be some like a natural weather, like for the lightning. It can also produce the interference to our system. And for the TV receiver over here, so we have this idea, there's some source of the noise coming through the wall, the guys working on the next door, and the interference would coming through the AC line over here. And the interference also the frequency dependent. So it's, in some range of the frequencies will be really difficult to protect. And how about in the railway system? We start from the left to the right. Okay. Over here, that in the past we have just the to do the operation. So we only have the train with just a simple electromechanical device or equipment, like a just simple one, or some of them that install inside the station. But as the time process, so we have new generation of the railway system, because we need the higher speed with the better technology. So we're going to involve a lot of electronic and electrical components, and as you see by the pictures. And this kind of the equipment, they would interfere each other. Not only each other, it also between the railway system and external environment. Okay, this is quite important. And if we're talking in the railway system, a good EMC, we need a good EMC for what? First, of course, for the safety of the person. This is sitting on the top of the list. Yeah, we put the high priority on the safety of the person, and the protection of the equipment and the installations. And to achieve the targets, we need to follow the good standards, and of course, a good engineering practice for the installation, like for example, the earthing and bonding. And all of them will be managed through what we call the system assurance planning. Okay. But we're going to focus in this presentation about the influence on the external environment, and how the subsystem can interact to each other. So this is what we're going to focus in this presentation. And for the big picture of the EMC, we have the system-wide interaction. When we consider to have the good EMC, first we checking the interaction within each individual subsystem first, and then interaction among subsystem, and finally the interaction between the railway system and the external environment. We have to make sure that all of the interaction, they are under the limit based on the standard recommendations. Okay, so you see how the local R&D can be part of the railway construction. And this is the traditional project life cycle diagram based on the EN 5126, or we would call it the V cycle. It's a typical V-shaped diagram. It starts from the top left over here and all the way down and finish on the top right over here. And when we started the project, we start with the project requirements, maybe from the tendering process. So we have the big picture of the requirement. Then what we're gonna do, we're gonna do the requirement allocation to many subsystems before we start doing the design. And we have so many steps during the design phase over here. So we have all kinds of design. Maybe start with just the overview of the design, but finally we're gonna get the details of the equipment after the design. Then we're gonna visit the manufacturers, start doing the installation, and of course the testing and commissioning right after the installation. And before we hand over to the operator, so we're gonna do some of the trial runs of the train. And we're supposed to have the EMC activity start right at the very early, at the very beginning. So So we can start during the design period over here before installation, because if something wrong with the design, so we cannot stop the installation. Okay, so we're gonna have start early during the design, and this is the infrastructure, or we call the fixed installation, to be implemented. It's not implemented yet, but during the design, we thought, oh, okay, this kind of the layout that we're gonna implement in the project is look complicated, but it's still okay, because just simple infrastructure, like a lot of the catenary system. Yeah, what do we do? We're gonna have to identify some of the external source of the interference. For example, we have the distribution line, AC line over here. We have transmission line system, transformers, of course, and tall radio tower, and some of the tall buildings next to the railway corridor. This could be the potential source of interference. Okay, not including the lightning, but discounting like can cause a malfunction of our system. So what do? We would do the survey, okay, and even on top of the survey, we can do some of the measurement, and to make sure that this kind of the interference is still at the acceptable level. And what do? We would again confirm with the by running the simulation, and we have some of the commercial available software, like the first one over here. We can do the simulation of the catenary system, or this is in case of we have the transmission or distribution system in the middle of two tracks, or we can do some simulation for the magnetic flux density inside the station, just a simple one. Okay, we have the commercial software to support, but if the installation is this complicated, lots of cable trays, maybe the commercial software cannot offer these kind of details. So that's why this is the room that the local research can be part of the can involve with the project implementation. We start and it start early during the design phase, and this is a picture of the one of the project in Bangkok. So we have the civil work over here. We have the concrete infrastructure, the pier. We have the concrete beam, and interestingly, we have the sort of the interference just right next to our infrastructure. We have 115 kV and 24 kV distribution system, and it's quite close. Okay, and between the guideway beam over here, this is the aluminum walkway. Yeah, but we're gonna focus over here the cable tray, because inside the cable tray we have so many sensitive components like the signaling cable and the equipment. So we need to confirm that is the level of the interference from this source, it will be low. Okay, but again, the system is quite complicated over here. So if we need the higher good result with the higher resolution, what do we do? Just we have that simply doing the meshing over here. Okay, and but doing the whole matching simulation is gonna be time consuming. So if we're gonna focus only the certain area of the interest over here, maybe it's gonna be just the small portion over here. And we're going to check the interference, the impact from the interference to the location that we focus. But first, we need to identify the source of the interference. And we, based on the IEC 6909, so we have the procedure to identify the short circuit current of the distribution line. And since the current over here is quite far from the focus area over here, so we're supposed to do the what we call the magnetic vector potential over here, like not the actual current, just the another image of the currents over here, and along the surface of the small area over here. Then okay, this is the engineering information over here. We have some of the equation over here, the Poisson equation. And once we get the new source of the interference along the border over here, so we do some calculation inside the focus area over here based on the finite difference technique. And the big information over here represents just a single cell over here. And this is what we have. This is the distribution of the vector A, or the magnetic vector potential. Now we have we focus on the source on the border of the focus area over here, and then we're doing further on the calculation underneath the small area over here. Then we get the distribution of the magnetic flux density based on this equation, and taking into account all the eddy current, all sorts of information. But it's not done yet, because there's something else. We need to put some interaction between the infrastructure and the railway traction. So this is the diagram of the system with the two traction substation, and this is the equivalent circuit. And we're doing the train movement simulation with the DC power flow simulation with the coupling mechanism from the previous magnetic flux density. And yeah, we introduce the what we call the induced EMF on the system, and this is the part of the modeling the coupling mechanism. And finally, we get the traction current over here under the external influence from the AC power line. And we have this current to do a little bit more calculation over here. Actually, we need to identify what we call the impermissible area. It means if we need to install the equipment, we have to avoid the shaded area over here. The white area, that this is the safe area that we can install the equipment. For example, inside the cable tray it is good to put the cable and the equipment. Okay, this is based on the 5121-4, but for the safety of the person, so we have another standard. Now everything ready, good to go. Okay, so we move to the installation, and for further reading, you can up here. Okay, this is just the first part of the how we put the R&D. Okay, we say time up, but a few more minutes. Another location that we can have the R&D, the part of the project, is over here after the testing before the trial run, and this is the complete set of the layout of the system. Yeah, we have the train ready, everything all set, ready to go, but we need to confirm that it's not going to produce any interference to the community along the railway alignment. So what we try, we put the sort of the interference, the theta radio antenna working at the 400 megahertz over here. Of course, again, first we energize without the tail running, just after energization. Again, we doing the grading, okay, and some calculation. And then we have the profile of the distribution of the potential across the component and the infrastructure. You see, we have the traction third rail, and we have the running rail, and yeah, this is after the energization. This is what we have, which is not visible. Okay. Then we need to check the wave propagation caused by the antenna over here. So based on the finite different time domain technique, and it is from the Maxwell equations that most of us already running through the equations from the engineering school, and do some calculation again, and also checking the radiation from the system. We're checking at the first location, O1 is just about the same level of the train, and O2 about maybe represent the community area right after the viaduct. And we have the profile of the electric and field and the magnetic fields. Actually, both of them will start simultaneously, but I just show this separately. And therefore the radiation pattern. So if you compare with this layout, you see like it's going to be more like radiation toward on the left of this infrastructure, because the train sitting on the left track, and you see that we're going to have less level of the radiation over here, because underneath the railway we have some kind of the reinforcing steel that will be protect the radiation. And of course, we do need to do the validation based on EN 5121-2, and we have this kind of setup based on the standard recommendation. And if you remember, we focus on the antenna working during 400 megahertz. So this setup will be perfect. We fit in our purposes. Okay. And this is the limitation of the because we have to make sure that we're not going to disturb the community along the railway corridor, and this is our limit lines, and we have many curves over here, but we focus on the curve C. Because curve C is for the metro system, because the train will be running through the heart of the city, and the safety of the people will be quite important. So we have quite a tough limitation over here. And this is from the experiment. For you see the solid line. We have the behavior compared with the simulation is quite matched, but at the center frequency or at the high frequency, it's start to see some difference, because maybe at the high frequency we have this higher absorption, maybe from the environment. Okay, but this seems okay. Now we can predict what's going on after the railway going out for the service. And further reading over here. And this is the activity during the SIT. And this is train running. And this is we checking the profile of the interference. This is for the purple line next to the building. This is maybe 10 years ago. And now I conclude the presentation. Now we have seen like we see a lot of complication during the system implementation. So we're gonna need the good scheme, the good EMC management, and we have seen that we finally can support the project construction by the local R&D. Okay, yeah. I think that's pretty much for my presentation. Thank you.
Thank you so much, Dr. Phumin.
Sorry.
So, any question? Maybe just only one if you have. Or otherwise, thank you so much.
Thank you.